This is the fundamental theorem of calculus part 2, and in many ways this is really the meat and potatoes of calculus 2. This is what we do all the time. So this says to evaluate the definite integral of f of x from a to b, we can evaluate big F of b minus big F of a, where big F prime is equal to f. In other words, to evaluate a definite integral, find an antiderivative, plug in the limits, and take their difference. You take the big F of the lower limit, subtract that from big F of the big, upper limit. Here is the proof. I'm not even going to write proof there, just I suppose maybe not to freak you out, but here's the deal. Let's let g of x be the cumulative area function of f from a to x. Then on the one hand, the fundamental theorem of calculus part 1 says that the derivative of g is f of x, and big F also has derivative f of x, so g prime and big F prime are the same. Then one of our facts of antiderivative says that g and big F differ by a constant. Say g is equal to big F plus some constant c. Then let's evaluate the integral. The integral from a to b of f of x dx is, by definition of g of x, this is g of b, because g of b is the cumulative area of f from a to b. Well, g of a is equal to 0. Note that if I plug in a for g, I get the integral from a to a. So I can just subtract g of a here because it's the same thing as 0. So this line and this line are the same. Now g of x is f of x plus c, so g of b is big F of b plus c, g of a is big F of a plus c. If I distribute this negative here, I get negative f of a, negative c, c minus c is 0. So I'm just left with big F of b minus big F of a. Great. So this is exactly how we're going to be evaluating definite integrals throughout this course. Okay, so let's return to what is pretty much the first problem that we looked at in all these videos. The integral from 0 to 1 of x squared dx. How is that the first problem we looked at? Well, interpreting the definite integral in terms of areas, this is saying let's find the area under x squared above the x-axis between x equal to 0 and x equal to 1, right there. That's precisely it. So the fundamental theorem of calculus part 2 says first, let's find an antiderivative, say x cubed over 3. That's the simplest one to work with. All the other ones look like x cubed over 3 plus a constant. Why add 2 to that? It's much easier just to have x cubed over 3. Okay. Then we plug in the limits. So the integral from 0 to 1 x squared dx is, we write this expression over here. So generally, if I'm going to write f of x, and I write a line a, b like this, this means take f of b and subtract f of a. So it's just sort of a nice shorthand way of being able to write down the antiderivative and then reminding ourselves that we have to plug in the limits of integration. Okay, so I plug in 1, I got 1 cubed over 3 minus 0 cubed over 3. That's 1/3, and that is precisely what we thought that the area was as we let the number of subintervals go to infinity. But now we have a much cleaner way of doing it. In fact, this is pretty much the right way of doing it. Let's do one more question, an example rather, and then one more question for you guys. So let's find the value of c such that the integral from 1 to c of 1 over x dx is equal to 1. This is really more of a variation on what would typically be a Calc 2 problem. Typically you're given the limits and you want to find the value. But here I'm giving us the value of the integral and I'm asking us to figure out what limit gives us this. So really you can interpret this as what is the value of c such that the area underneath the curve 1 over x from 1 to c is equal to 1. So An antiderivative of 1 over x is the natural log of the absolute value of x. And this is going from 1 to c. So I plug in c and I plug in 1. And I get the log of the absolute value of c minus 0 because the log of 1 is 0. So I'm just left with the log of absolute value of c. So this area is equal to natural log of the absolute value of c. So 1 is equal to that. If that happens, then c has to be equal to e, because the natural log of e is equal to 1. And since this only makes sense if c is positive, you can't take this integral for negative c. Yes, we are allowed to have a smaller limit of integration up top. However, we wouldn't be able to integrate because 1 over x is undefined at 0, so our interval can't contain 0. So if the absolute value of c is equal to e, then c must be e. So e can actually be defined as the value such that 1 to e, the integral of 1 to e of 1 over x dx is equal to 1. Okay. Finally, here is one last question for you guys. I want you to evaluate the following definite integral using the fundamental theorem of calculus, part 2. Integrate from 0 to 2 pi cosine x dx. And I'd like you to interpret your answer. Explain why it is what it is in terms of areas under graphs of functions.